Hello class, and welcome to today's video on sections 2.1 and 2.2, which are covering input and output, domain and range. Please make sure you take good notes and write down the summary of the video, as well as don't forget to submit your summary and a top question to your online whisk the day before class. Now let's get started. When we evaluate a function, all we're doing is calculating the value of the function's output from a value of input. So, for example, let's say I have a function that looks something like this, and I want to evaluate that function for x equals 3. Okay, so to evaluate it basically means most of the time substituting the value into the function. So in this case, instead of an x, I'm going to input 3. So I'm going to multiply this 3 times 3, and my evaluation implies that f of 3 is going to equal 11. That's what it means to evaluate a function. Determining the output, and this is the output, from the input. Okay, now sometimes you may see the function represented as y equals, but you have to understand that y and f of x represent the exact same thing. Oops, y and f of x. Okay, all right. Now let's see about, we know about calculating the input from the output from the input. Now let's see about how do we calculate the input from the output. In other words, how can we determine the value of the function's input if we already know the output? So let's take back a look at our example of f of x is equal to 3x plus 2. And let's say that I know that f of x is equal to, let's say, negative 5. So then the question is, which x makes that a true statement? Well, that's called solving the equations, and you're familiar with that. We set the value, the function value equal to the function, and then we work our way backwards to isolate x to get x by itself. So during our algebra, we end up with 3x is equal to negative 7, and we divide by 3, and we get that the x that works is negative 7 over 3, which means that f of negative 7 over 3 is equal to negative 5. So even though this is our solution, negative 7/3, we can check our solution by plugging it back into the original function and calculating it, sorry it's so messy, to see do we actually get negative 5. And in this case, we will get negative 5. So I know the algebra was very simple, but I want you to focus on the definition and the vocabulary, which involves evaluating a function, and then it also, and it also involves, after evaluating the function, solving a function, or solving an equation to be more specific. And solving an equation, is the same thing as finding input values. So now let's take a look at how do we find input and output values from tables and graphs. Instead of using algebra to determine the input and output, how can we find this out from tables and graphs? So here we have a table, and if I want to find the output for a particular input where the data value is already in the table, all I have to do is say, well, if they want to know if the input is 4, what's my output? I just find 4, and then I can determine the output by looking to the right. And what if they say, well, what number of days will give you $55? Well, I go and find $55 in the output column, and then the resulting answer is to the left, which is input. And that's easy enough, but what if I want a value that is not in the table? So for example, what if the input is 5? So when input is 5, how do I figure out the output? Well, if it is in any type of pattern, we know that the 5 should go somewhere in here. So it seems like if this is a function that we're used to, then our answer for our output should be somewhere in between 30 and 40. So our output, we can estimate it to be between 30 and 40. Okay, now that might not always work depending on the type of function that this is, but it looks pretty much like we can, this is a linear function because of the rate of change. But for right now, we can say that the output is in between 30 and 40. So you can find the input and output from values that are in the table and values that aren't in the table. The only thing about values that aren't in the table is that you're going to get an estimation and not an exact number for sure, unless you change the table so that it includes 5. Now it's a little bit easier to find that information from a graph than a table, because a graph has more information. You know, a picture tells you 1,000 is worth 1,000 words. So let's say, for example, I know that I want to find the resulting output for when V is equal to 0.8. Well, I call it the vertical line test. It's not a vertical line test, but the vertical line property, which is I will go over here to where V is equal to 0.8, and I would draw a vertical line. And wherever the graph intersects V, that would be my solution, that vertical line, which is right there. And so then I would say, well, what is that value going over here? It looks to be somewhere around 2.5. So I'm going to say 2.5 because I don't know exactly what it is. So even though you have more values on a graph that you can see, your values may not be as accurate because as they would be on a table, and that's a disadvantage. Now, what if I know what I is and I want to find out what V is? Well, instead of using a vertical line, I would use a horizontal line to find that exact value. So let me get rid of this. Oops, and let me look at a vertical line. Let me get a vertical line to do the exact same thing. So this time I want I to equal 10, so I go to where I is equal to 10. And then what I see is that it seems like right here, where the horizontal line intersects the graph, is my point, and I have to figure out what that is. And that's like around 1.8. So we use vertical and horizontal lines to be able to determine the related input and outputs from graphs. Now you don't actually have to draw a vertical or horizontal line. Sometimes you can use your finger to go over it, you know, like what I'm doing, and then determining your answer. But you can find input and output values from tables and graphs using those strategies. And now we're going to talk about section 2.2, domain and range. And if you recall, if Q is a function or F is a function, the domain of F is a set of all input values which yield an output value. And the range of F is a corresponding set of output values, Q. So if I have a picture like I have here of a function F, then the domain would be representative of all the input values that this function has. And in this case, all the input values are between A and B, wherever A and B may be. There, if I pick an input value that's outside, like somewhere over here, that's not part of our domain because I don't have any function above or beneath it. So the domain is any x value that has a part of the function directly above or beneath it or on it. That's another way I describe a domain. And we usually describe a domain because there's so many numbers as an interval. So in other words, I could describe this domain as any x value between A and B, or I can say the interval from A to B, including A and B. So that represents the domain of the function. It's a bunch of values, and sometimes it's easy to identify each individual value, but most of the time it's not. Then the range is the corresponding output values, as we see, that are resulting from this domain. So here is my range, because as I can see here, my output values to the left or to the right are in between these values. Okay, so the range would be the corresponding values, and in this case I can say this is f of A and this is f of B, even though I don't know their exact value. So the range depends on the domain. Now the problem is sometimes there are functions that have domain input values, but there's one input value that's not available, and we'll talk about that in class. Now if I have a value, say for example, that's not in my domain, so let's say this is C, And I know that it's not in the domain because if I were to erase this piece of the graph and there would be an open hole, then that means that value C is not in the domain. So C would not be in the domain. It's not in the domain. That means not in the domain. But there's a difference between the value not being in the domain and us restricting the domain. So let's take a look at that. So here we have an example of restricted domain and range. And it can be restricted for a variety of reasons. It could be a realistic situation, like maybe even though the domain can be from this point to this point, maybe in our particular situation, we're only considering these values. So that's what restricted domains are, and they're really for real life situations where the function describe the situation, but we have too much extra stuff. So in this particular example, the domain is restricted, even though we can continue the graph going on right here. And we'll take a look more about that in class. So I just wanted to give you an idea about what a restricted domain and range would be. And in this case, this is the restricted domain, and this is the restricted range, even though the real function has a domain that's wider than that, and the real function has a range that's wider than that. Okay, that's it.